Hi, welcome to Technocode. Our today's topic is simple linear regression through R. But before we jump to actual topic, let's hold back and see what is simple linear regression. A simple linear regression is a predictive modeling technique where we try to establish a linear relationship or a mathematical equation between a predictor and an independent variable with a response variable or a dependent variable. Now that we have seen what is a simple linear regression, let's jump to our topic. The dataset which we will use today for our topic is an inbuilt dataset. The name of this dataset is cars. This cars dataset gives us the speed of the car and the distance it took to stop it. You can find more about this dataset in this screen. You can come to this screen by simply typing question mark cars in console and running it. Let's have a closer look of this dataset. Let's first view the first 6 lines of this dataset by using head command. So these are the first 6 rows of cars dataset where it has only 2 columns, speed and distance. Now let's go ahead and do the summary of this dataset. So this is a short summary of this dataset where it tells us that we have 2 columns. One is speed, other is distance. The minimum value in speed is 4, the maximum value in speed is 25, the minimum value in distance is 2, the maximum value in distance is 120 feet. As we can see, the median and mean is approximately same in case of speed, which means that the data is normally distributed or equally distributed. So we won't go in that part right now in this video. Let's go ahead and jump to our main topic. Now before we go ahead and start with building our simple linear regression model, we need to first check whether there is actually some relationship between our variable or they are just random. The easiest way to check this is scatter plot and correlation between our two variables. Let's first see the scatter plot. Cars speed on the y-axis will have a distance. Let's just give the title to our graph. Let's just okay, so this is our plot. From the plot it is clear that there is a linearly increasing relationship between our two variables. This is a good thing because the underlying assumption of linear regression is that the relationship between the response variable, that is in our case is speed, and the predictor variable, that is in our case is distance, should be linear, and this is a linear relationship. So we can safely go ahead and apply the simple linear regression on this data. Also, before jumping to next part, let's also go ahead and see the correlation between uh, these two variable, which will tell us the level of linear dependency between our two variable. correlation cars. So the correlation between speed and distance is about 80%, which is fairly good enough. Now there is one more important thing which we need to do before we jump down to our main topic of building simple linear regression. The important thing which I'm talking about is splitting the data into 80-20, wherein we'll use the 80% data to build our model and rest of the 20% will be utilized to test our model. In this way, we'll come to know that how our model is working when we will provide a new data to it or an unknown data to it. So let's go ahead and first split the data into 80-20 format. Okay, so we'll go ahead and use sample function and we'll pick up the random 80% row numbers from our total row numbers. Size, we want 80% of row numbers, so 0.8 into total number of row numbers, which will get from n rows of cars, and whether we want to take it with replacement. No, we don't want to take it with replacement, so replace is false. So now we have randomly taken 80% of row numbers from total row numbers. Now we'll use these row numbers to form our train and test data set. Cars, row numbers. And test will not pick up those rows numbers which we have selected above, so we'll apply minus sign over there. Let's just quickly check the dimensions of our both train and test data set. So our train data set have almost 40 rows and 2 columns, whereas our test data set have 10 rows and 2 columns. So now we have successfully splitted our data into 80-20 format, where 80% of the data is present in the train dataset, while the 20% dataset is present in test dataset. Now we move on to our main step of creating a simple linear regression. Okay, let's start with it. SLR model is equal to LM for linear model. Our response variable is distance. Our predictor variable is speed, and the data which we have to refer is our train data, that is 80% of our original data. So for building the simple linear regression model, we are using the function LM. The LM function takes in two main arguments. namely the formula and the data, which is typically in data frame format. You're seeing here. So this is our data part and this is our formula part. Okay, so we'll just go ahead and run this statement. So now let's view our SLR model. So this is our SLR model. The model tells us that the intercept of is minus 20.47 while the coefficient of speed should be 4.06. So now as the linear model is built, but is this enough to actually use this model? The simple answer to this question is no. The reason behind that is because before using a regression model you have to ensure that it is significant enough to be used, and more importantly it should be statistically significant. So we'll go ahead and find it out by doing a summary of model. Let's just run this statement. Okay, so this is a summary of our model. The first statement is the same which you have provided over here. So it is basically contains what call or what formula and data which you use to create this model. The important part is the p-values which is present over here and here. The p-value is for checking the statistical significance. This summary tells us the number of things. One of them is the model p-value, that is one which is present at the bottom line, and the p-value of individual predictor which is present in the last column. The p-value are very important because we can consider a linear model to be statistically significant only when both this p-value are less than the predefined statistical significance level, which is ideally 0.05, that is 5%. This is usually intercepted by significance star at the end of the row. The more the number of stars, the more the significant variable it is. The next information which we have to look in this summary is R square. The actual information in the data is the total variation it contains, right? What R square tells us is the proportion of variation in the dependent or response variable that has been explained by this model. Now the next question is, when we have R square, what is the adjusted R square about and what is the use of it? The adjusted R square uh, the adjusted R square is more significant than R square because uh, as you add terms in your model, the R square value of the new model will always be greater than the subset. This is because since all the variables in the original model is also present, the contribution to explain the dependent variable still remains in the superset, and therefore whatever new variable we add, whether it is significant or not, whether it is useful or not, the R square value would still increase. To counter this problem, we have a adjusted R square which will help us to solve this problem. Adjusted R-squares penalize the total value for the number of terms we add in our model. Okay, so uh, from the model it is clear that uh, the p-values, both the p-values are significantly low, and so we can go ahead and create our simple linear model, or in fact go ahead and use our simple linear model which we have created to predict our values. So now to predict our values of the test data set, we'll use the function called predict. So we'll first create variable predict. The distance is equal to predict. We'll use our SLR model which we created above, and this time our data would be test data. So now we have predicted the distances of the test data set which we have. Now let's go ahead and check whether the predicted value are equal to our actual values, or if there is an difference, how much is that difference, and whether our model is working right on new data or not. A simple way to check this is a simple correlation between actual and predicted values, which will give us the accuracy measure. The higher the correlation accuracy between the actual and predicted value, the better our model is. Correlation for actual values is test dollar distance comma spread distance. So let's see the correlation accuracy. So our correlation accuracy is almost 76%, which is fairly good enough. Now we'll go ahead and check what is a map in our case. Map is nothing but mean absolute percentage error. Okay, so our map is almost 57.46. Now let's I have placed the heading long. Let me correct out those heading. This heading should come over here, and this heading should come over here. This should be over here. So this is our complete code for simple linear regression. That's it for now for simple linear regression. Thank you. I hope you find this video helpful in some way. Please like, share and subscribe for more such videos. Thank you.